So the normal distribution. If you have some continuous data that all centrals is clustered around a particular central value or mean, and it makes a nice bell curve. Isn't that pretty? That one's actually really nice. Those properties describe something called a normal distribution. It's defined by two parameters, the mean and the variance. And when it's normally distributed, this is what we write. So we write our mean and our standard deviation, and we use the n to say it's normally distributed. Notice we had something before this that was similar. We had a binomial distribution with a b there. Now we have a normal distribution with a bell curve. The total area under that curve is 1. Now it's a fascinating curve because technically this bell continues on forever this way and continues on forever that way, never touches the x-axis, but it gets so close to it that we can say that the area is 1. You've done infinite things before with geometric sequences. Remember the infinite geometric sequences? That even though it went on forever, it still had a value that it went to. This is sort of a similar idea. Even though that bell continues forever, it is, the whole area is 1. And it represents probabilities. So a couple things about this. You've got your standard deviation, your mean is always right here in the middle. And then we measure things by counting how many standard deviations things are away from the mean. And so a standard bell curve will usually show 3 standard deviations above and 3 standard deviations below. The following things always happen with a normal curve. These percentages that you see there represent the chances of something happening. So if you wanted to find what are the chances that if I randomly pick someone and I'm looking at data that fits a normal distribution, say heights, the heights of different people. If I randomly pick someone and I knew the average height was 150 centimeters and I knew that the standard deviation was 8 centimeters, the probability that if I randomly pick someone and their height was between 150 and 158, that would represent this shaded area right here. And in our diagram, it says that that chance of that happening is about 34.1%. Roughly 68% of the data is between 1 standard deviation above and below. So most of the people, 68%, would fit in that range. Once you go to 2 standard deviations away from the mean, you've got 95% of the population. Sometimes this 68 and this 95, I've seen it written in some textbooks as the 68, 95, 99.7 rule. It's got a nice ring to it. And it's to help you remember that if you go 1 standard deviation, you have 68%. If you would go 2 standard deviations, you would be 95%. And if you would go all 3 standard deviations, you're almost at 100%. Oh, my lines don't quite match up, but that's the idea. So if you have a normal distribution and you know the mean and the standard deviation, you can say almost 100% of the population is between these 2 values. And for things that happen like heights and people's weights, generally they'll fit a normal distribution. There is still the possibility of that person that's 8'10". That's way, way, way outside. And that's why that line continues that way. But the chances of that happening are very, very unlikely. Right? I've never had a class where someone was 8'10". I've never had a class where someone's been 7 feet. But it could happen. But that would be past 3 standard deviations. So normally we have our data, and then we also have something called a standard normal distribution. What we do with a standard normal distribution is we say, well, whatever we decided was the mean, so before I said that 150 centimeters was the mean for height, we just make the mean 0. And instead of counting the actual numbers that we go up by, we just count by standard deviations. So standard normal distribution would have a mean at 0 and then a variance of 1, which would also mean that your sigma would be 1 as well. Okay, and here is a graph of your standard normal. And we call all the values on our standard normal z-scores. So if something has a z-score of 1.32, that would tell you that they are 1.32 standard deviations above the mean. If someone had a z-score of negative 0.8, that would tell you that you have a score that is 0.8 standard deviations below the mean. And of course, with all of this stuff, we do a ton of stuff with our calculator to figure things out. You don't have to write this down, but if you're interested, that's a yellow dot on a blue square. If you're interested, that is the actual formula for that bell curve. It's so pretty. It has 3 variables, an x variable, a mean, and a standard deviation. It's got the number e in it, which is kind of cool. And every time you have a normal distribution, the mean, the median, and the mode are all the same because it's symmetrical about the mean. So the area under the curve is exactly the probability of something happening. So we're going to take out our calculators, and we're going to find normal CDF. I'm going to clear out the stuff that I have on here. Ooh, do I have stuff? All right. So normal CDF, you're going to put a lower bound and upper bound, and then you're going to calculate, it's going to calculate the area under that curve. So here's our first example. One of the things that I find really helpful is to draw a quick bell curve every time you're asked for a question. So here we've got chest measurements of 18-year-olds with a mean of 95 and a standard deviation of 8 centimeters. It has a normal distribution. So what that means is we can draw a bell curve. The mean is 95. You put that 95 right in the middle. The standard deviation is 8, so we can add 8 3 times and subtract 8 3 times. So that'll make this 103, 111, 119, 87, 79, and 71. So there is your mean in the middle, and you've gone up 3 standard deviations and down 3 standard deviations. And now we want to find what are the chances that someone was between 87, right there, and 103. Now from the 68, 95, 99.7 rule, you should be able to say, I have an estimate for this. This should be around 68%. Now we're going to find from our calculator exactly to 3 sig figs, because on your exam you'll need 3 sig figs, so 68% won't be quite enough. So we'll go normal CDF. We're going from 87 to 103 with a mean of 95 and a standard deviation of 8. So where is that on our calculator? Again, go to distribution, same place that you found binomial PDF and binom CDF, except you see them right away. Your lower number was, was it 87? And then 103, 95, and a mean of 8, or sorry, standard deviation of 8. It pastes it in there for us. So this is what you would write on a quiz or test to show your work from your GDC. And we get 68.3. That means there's a 68.3% chance of this. And in fact, when you draw this in, I've drawn the two lines there. I should have also shaded this in to represent. That is the area. That area is 0.683. Now, if you would like to draw this to get a visual of this as well, you can. It's really quite tricky. So we'll get this here. What we're going to go back to distribution. And beside distribution is draw. So if you go over to draw, you can shade a normal curve. If you push enter on that, again, our lower one was 87. Our upper one was 103. Our mean was 95. And our sigma was 8. Again, if this screen doesn't come up for yours, you'd have to go shade norm 87, 103, 95, 8, and then go to draw. And nothing appears because your window is set from 10 to 10, negative 10 to 10, and from 10 to 10. What you need to draw on your window is exactly the same thing we drew here. So if I want to see this curve, I'm going to need to set my window maybe from 71 to 119. So we'll do that next. We'll just change our x coordinates. Go to our window. We'll go from 71 to 119. That'll show us our 3 standard deviations. Since our standard deviation is 8, it's going to be nice if we set our scale at 8. I don't know. We'll see if it matches up nicely in the middle. It might not even match up nicely in the middle. But we're going to try and graph this now and be disappointed one more time. Okay. Oh, and now we're really disappointed because nothing showed up. Every time you change your window for shade norm, it erases your drawing. So what do you have to do? You have to go back and highlight it again and push enter again, and then it shades it again. And once again, we're disappointed because it looks just like a straight line. That doesn't look like a very nice bell curve. The reason for that now is our y-scale goes from negative 10 to 10. Remember, the area under our curve is 1. So if it went as high as 10, you'd have a huge area under that curve. So now we're going to have to go back to our window. We don't need to see anything in the negative. I'm just going to put negative 0.1 just so that I have my axes still appear. And my y max will start with 1. Because we know if it was higher than 1, you would still have way too big of an area. Now we push graph once again and go, oh yeah, it erases it, and get disappointed. So we go back to here, do this again, and we see a bit of the bell curve But I hope you can see that going up to 1 is still quite a bit too much. In fact, if this is 1, halfway would be half, a quarter. We could probably get away with 0.1. So I'm going to go back to my window, change my Y max to 0.1, quit. This time I was smarter. I went back to shade norm before I hit graph. And that does look like a nice normal distribution. That's pretty. Yes. Yours is not working. I'll come check it. All right. So now we got part B. What is the probability 18-year-old has a chest measurement less than 87? So we quickly redraw our normal distribution, just like that. Yeah, you just, what I did is I did hold your finger on your picture and just drag it down. It should just reappear. Or if that doesn't work, at least you'll get some pencil smudge on your finger. And now we want to find probability has less than 87. So now we're going to color in this section right here. So second distribution, normal CDF. Now, do you remember when we had this the last time? Do you remember seeing that it had this in there? Okay. That's basically the closest thing you have to infinity. Right now, we would like, I'm going to insert e to the 99, oops, I want to keep that e to the 99, and I'm going to put a negative, in front. Now, that's the closest thing we have to negative infinity. Because e to the 99 means times 10 to the power 99. So that's going to make that a very, very small number way, way down. Now our upper bound, since we're going from negative infinity, we're going all the way up to 87. Our mean and our standard deviation are still the same. And we're going to paste it in here. We're going to get that percentage. Now if we had to guess, from what we had before, okay, this is what I would do as an estimate. So, okay, I'll just write down what we wrote in. Normal CDF, we had negative 1 e to the 99, comma, up to 87, still 95 and 8. And to 3 sig figs, we got 1, 5, 8. Is that right? 1, 5, 9. As far as an estimate goes, since you know the 68, 95, 99.7, first of all, half of it's 50%. So you know it's not going to have that 50%. And we learned that this was 34%, or on the one that was more accurate, it even said 34.1. So these two red ones together make 84, which would leave 16% left that's shaded. And that's roughly what we got. We got 15.9%. If you use 34.1, because you're really good at remembering decimal places and you're like, that's just stuck in your head, then 15.9 actually works out perfectly. So now, what is the probability an 18-year-old has a chest measurement greater than 87%? Oh, we should just graph let's graph this one just to get the shading. So I'm going to go back to my calculator just to practice our shade norm. I want to show you something interesting that happens. So we go back here, oops, go over to draw, shade norm. Notice the -1 e to the 99 already came up. That's kind of helpful. The upper was 87, mean of 95, standard deviation of 8. And we go to draw it. And the last one didn't go away. Every other time we did something, the last one went away, and it was frustrating. Now the last one didn't go away. And now it's frustrating again. So if we don't change our window, our drawing doesn't go away. If we change our window, our drawing goes away. So to get rid of a drawing when you want it to go away, and it's still there, we can go above the program button, you see the word draw. You go second draw, and the very first one is clear draw. That clears it away. Of course, now both of them are gone. So we have to go back to shade norm. And now it's gotten rid of all of our data. So instead of doing that, I'm just going to go back here and push enter again. And now it's drawn prettily. I don't know if that's a word. Prettily? Pretty nicely. There we go. All right, so the last one's probability that the chest measurement is greater than 87. We actually don't need to do anything on our calculator here because we've done work. Oh, that's fun to color. Why don't I have to do any calculations on my calculator? Right, we have the probability below 87 was 15.9%. So we could just do, since we know the whole area is 100% or 1, minus the 0.15. I guess I'm using an approximation, so I should go with my approximation sign there already. And I will get, oops, 84.1% or 0.841. Of course, you could do it with your calculator. Normal CDF. Now my lower one is 87. My upper one, if I want that to infinity, I'll use positive 1 e to the 99, comma, 95, comma, 8. And you'll get your percentage, 0.84134474404. Now, these are chest measurements. And we just put from 87 centimeters up to like 1 billion centimeters. A huge number, infinite, right? You can just imagine that guy walking down the street with that big of a chest measurement. It's really crazy impossible. In fact, we went up 95, the standard deviation is 8. So once we look at our graph, once it's past 119, there's very, very few people out there that have chest measurements bigger than 119. So even if we had not done infinity, so I'm going to retype this, and instead of doing the infinity here, even as small as going up 5 standard deviations. Standard deviation was 8. 8 times 5 would be going up 40 from our mean. Our mean was 95. So even if I went up to 135 instead of an infinite number, look how much the percentage is different. It's not until we go to 7 decimal places that it's actually different. And if we're doing things to 3 sig figs, our answer there would still be really, really accurate. If we went up to 200, so chest measurement of 200 centimeters, that's crazy. Notice at 200, none of the decimal places are even different. So it's very, very, very rare to go beyond that. Okay, so there's a little bit about shade norm. Because the shade norm is frustrating, most students just go to, right, go to the normal CDF. If you can draw it yourself, you don't really need to see it on your graphing calculator. And in fact, you almost need to draw it yourself in order to set your window correctly on your graphing calculator. So you're going to find you're probably not going to use this shade norm very often, if at all. You will use the normal CDF a lot because it gives you your answer right away. So these chocolates are produced by machine, are normally distributed with a mean of 232 grams. That makes me think of a medium-sized bag of mini eggs. I don't know if that's the right portion, but that's what I think of. Now I'm curious how close a medium-sized bag of mini eggs are to 232 grams, with a standard deviation of 3.6 grams. Sometimes you're going to get an extra egg that pops in there. Sometimes you get a short one. Everybody's probably had an experience where you bought something, opened it up, and you're like, whoa, this is way more full than normal. This is awesome. And also the disappointment of opening up the chip bag, and you're like, really? Right? So you do get some sort of distribution. They're not all perfect. When it says, when it says 75 grams on the bag, right, you could take them out and weigh them. It probably isn't exactly 75 grams. Don't go and phone the company and complain. Okay? Probably what most companies do is if it says 75 grams on their bag, they probably aim for a mean that's like 77 or 78. Because there's people out there that think they're getting gypped, and they will weigh them and phone the company and complain. So if you say 75 and your mean is probably a little bit more, you'll get less complaints. Very few people, I got more than I was supposed to. I'm going to phone and complain. Doesn't happen very much. Anyways, we're off topic. Here we go. We got a picture. We can draw our nice normal distribution. Our mean is 232. That would go right here. We go 1, 2, 3 above, 1, 2, 3 below. And we have to add 3.6. So we go to 235.6. I'm going to run out of space here. We're going to get to 239.2. And 3.6 will give us 242.8. Okay? Sometimes with decimals, I'm okay with just drawing 1, 2, 3. And then I don't write the numbers in, per se, but it gives you an idea. Now, find the proportion that can be expected to be less than 233.91. So now I'm going to estimate 233.91 is right there. And I want to find less than, so I'm going to shade this region. That's what I'm trying to find. So put it into your calculator and see what answer you get, and I'll put the answer up in a second. All right, how did you do? Did you get 0.702 to 3 sig figs with your normal CDF? Excellent. Oops, I'm falling behind here. Try this one as well. So try it on your own. I'll draw out a picture as well. And when you went to your normal CDF, did you get 0.159? How did I know that answer without going to normal CDF? Where did we get this answer before? We got it a couple questions ago when we were from 1 standard deviation below. The normal curve is symmetrical. So if I have 1 standard deviation and above, it's the same as 1 standard deviation and below. Again, though, it's good to use your normal CDF. So you got a 16% chance if you decide to have a baby in the next couple years. You got a 16% chance that it's going to be over 4 kilograms, according to this data. So now we're going to look at our standard normal distribution, where the mean is 0 and our standard deviation is 1, and our variance is 1. And we get to questions that have this kind of notation. Find the probability that the z-score is less than 2.68. So again, as far as the visual goes, it's nice to draw your bell curve quickly. Now with the standard normal distribution, your mean is 0. Go up 3, down 3, and there's our curve. We want to find the probability is less than 2.68. So we go to 2.68, estimate where that is, shade in what we want to find. Go to our calculator. It already has the -1 e to the 99. Now we're going up to 2.68. Our mean is 0 and our standard deviation is 1. And you've got a 99.6% chance very high that your z-score would be less than 2.68. What's the probability z is greater than -1.41? So again, we go, where's -1.41? About there. We want to find greater than. And you're not required to draw the picture, although I find drawing the picture really helps you see what you're trying to find, and it helps you put the data in to your normal CDF better. So we've got -1.41, 1 e to the 99, 0, and 1. And you got a 92.1 to 3 sig figs. One more for you to try. How'd you do? So we have these first questions that we've been doing with normal CDF have all been ones where we're trying to find the probability of something. What are the chances that you get a baby between this weight and this weight? What are the chances that you get a baby that weighs less than this? What are your chances that you get a baby that weighs more than this, right? So all of these things so far have been questions that say find the probability, find the chances. So one of the things that you're going to have in your mind when you're going into questions is you're going to be looking for that. Is this a normal distribution? Is it asking me to find the probability? Because if you have those things, you know that you're going to use normal CDF. Now we get a second type of question now that the percentage is given. Someone's in the top 10%. Someone is in the middle 50%. What are those scores? What if I want to get in the top 25% in Canada, what score do I have to get to do that? So we use something called inverse norm, because it's going to take your normal distribution and work backwards and say if you know the percentage, if you know the area, the mean and the standard deviation, you can find out what those scores are. Something about it, it always measures from the left. So here, if we've got, let's say, just a standard normal, okay, and you put in 10%, it will calculate 10% here. It'll put 0.1 always from the left. So if you want to find the top 10%, you would have to put in either 90% to figure that out, or do the math of 10% and the fact that it's symmetrical to figure it out that way. But it's probably easier for you to use 90% rather than calculate 10%. And that's what happens in our first question here. We draw our little standard deviation graph. The mean is 60, 1, 2, 3 above, 1, 2, 3 below, 67, 74, 81, 53, whoa, 46, and 39. What score would separate the top 10%? So what we're trying to find is something that would separate the top 10%. So that area would be 0.1, meaning that this area on this side would be 0.9. So when we're putting our inverse norm in, since it's always calculating from the left, we're going to put our 0.9 there. Our mean is 60. Our standard deviation is 7. Go to our distribution. Inverse norm is the third one right under normal CDF. Our area is 0.9. Our mean is 60. Standard deviation was 7. 68.9, which rounds to 69.0. When you're writing that to 3 sig figs, you would include the 69.0. And that would separate the top 10% of the class. We're going to add a part B here. What happens if they said the middle 50%? What would you put into inverse norm to find? Because now you need the two scores. You need the score that has the middle, the lower part, and the upper part to get that middle 50%. So we're looking for this to be 50%. So one score, you have to find the lower one, you have to find the upper one. L for lower, U for upper. Again, our mean is still 60, and our standard deviation is still 7. For the lower one, what area would I put in? For this line, I need to know what this area is here. Can you see that that would be 25%? So I would put in 0.25, 60, and 7. For the upper one, can you see that it would be 0.75? Because you got that 25% plus the 50%. And then whatever scores you would get. Does anyone have those scores? 55.3 and 64.7.